yeah, this is the Pywr-WREW project. We're developing a water resources model for England and Wales, which we hope will enable strategic analysis of drought resilience for water supply infrastructure. So I'm sure everyone's seen headlines like this over the last couple of years or 5 years. Our advance in climate learning over the past decade has shown that droughts are affecting larger areas, they're lasting longer, and they're becoming more intense. And with this, there's a need to adapt our water supply infrastructure to mean that it can cope with these increased frequency and intensity of drought. And this challenge isn't insurmountable, we can cope, but in order to do that, we need to make some quite timely and important and quite difficult decisions. And in order to do that, our water companies, our regulators and government need to have a strategic overview of the state of our water resources, not just at a regional scale, but also at a national scale. And so, over the last 5 to 10 years, we've been working with the Environment Agency and Ofwat to develop a national model of water resources, which is called the Water Resources Model for England and Wales, acronym WREW. And we've used this to analyse large-scale drivers of change, so that's climate change, abstraction reform, changing demand, and really understand how future climate and future changes of demand might impact our water supplies. This model itself covers over 90% of England and Wales's population. It has over 300 strategic assets, so those are the reservoirs, the boreholes, the water transfers, the rivers, the groundwater abstractions, and also all the licensing constraints and operational rules that essentially control how water gets from source to end user. And we've used this model to understand a great deal about threats to future water supplies, but the issue is that this model, which is built in WREW, is using a commercially licensed software. So it can't be easily shared with stakeholders. It's fairly complicated, and as you can see, it's not easily deciphered. So it's quite hard to dig into the model and really understand what's going on. So we've had this funding from DAFNI to convert this large model into a Python-based model using the Python library Pywr, or I learned the other day it's Pywr, not Pywr, but I call it Pywr, so I'm going to continue with that. And unlike WREW, this is an open source dynamic Python library. It's been designed for network-based resource allocation, developed by the University of Manchester, and it's used internationally. So there are some really good pluses to using this model, and we think that by converting our WREW-based version into Pywr, we can start to really engage with stakeholders and try to understand dynamics of our water system. So Pywr itself, the model's described in a JSON document, so it can be opened on your desktop, it can be opened online, interpreted using something like a Jupyter notebook, and it essentially contains all the data that you need to define your water systems model, and in addition to that, it can read data in through external files. So use things like CSV files or Excel files, or perhaps more complicated files if you want to use those. So we've been developing this model over the last 9 months now. This is what it looks like, so it's far more interpretable. You can see exactly where your reservoirs are, how those connect to different demand centres. And so we've been slowly but surely developing this model and trying to sort of reproduce results that we've generated using the WREW model. Another Northumbrian water example, if we zoom into Northumbrian water, so this is the water system that supplies Teesside, Tyneside, Sunderland, Newcastle, we can see an aggregated version of the network. So this is at a coarser scale than perhaps the utilities would actually model their system, but it does a pretty good job of showing how water gets from source to end user. So there are several strategic reservoirs. If we take this one, this is Kielder Reservoir, which is fairly upstream, a surface water reservoir. What we have here is, for a historic time period, our simulations from data from the water company, so Northumbrian Water kindly gave us data of their simulated levels, data from WREW, which is our old model, and then data from simulations from Pywr. So we can see that this yellow line follows pretty closely actually what we were reproducing in our old model. It's not perfect. As you can see, the line sits a fair bit away above the water company simulation model. So there is some more improvement that needs to be done, but I'll get onto that because we've got an exciting collaboration coming up that will help us to do that. Take another reservoir, so here we have Derwentwre. This is an important strategic reservoir because the levels of service for Northumbrian water are set on this. So again, same time series, but this time we can see that actually Pywr in some key years is performing better. But so far, we're fairly happy we're able to reproduce at least the results that are coming out of the older version of the model. So why is this important? Why do we need to understand what's happening in our reservoirs? Well, often for water companies across the England and Wales and in Scotland, reservoir levels are used to determine whether or not customers might have to experience water restrictions, so things like hosepipe bans or drought orders. And so what we can do is we can look at this is a dynamic process, so if the reservoir falls below a certain level, then water restrictions, shown here with the red time series, are triggered, and this means that water demand is forcibly reduced. So you might have a hosepipe ban imposed, and it means that you can't water your garden in the summer months. And so that's why these models are quite helpful, because it means that we can understand dynamics in the water system, and then we can start to think about the strategic infrastructure that we might introduce to the system to help build the resilience of the system to these drought periods. So on DAFNI, just very simply, we Dockerize the model and all the data, we upload it, and then we can run the model and get outputs in the form of a HDF5 file, and then you can take that and you can generate some nice simple plots of different features of the system to really understand what's going on. And I have a demonstration downstairs, so if you want to come and have a look at what the actual model looks like and the outputs, come find me and I'll show you. And so, as I said, there are some parts of the model where we can definitely improve. So we're going to work with the USARIS project to try and understand what features of the model are causing those sort of miscalibrated or not perfect representation of our system. So I'm going to work with Saskia and the SAFE toolbox developed at the University of Bristol to really dig into those sensitivities and try and quantify some uncertainties that we're sort of representing. So what's next? We still need to Dockerize and run the model on DAFNI. We've got it running locally, but it needs to be uploaded. We're going to continue developing and testing the model for other regions of the UK. I want to put some future climate products through the model, so at the moment I'm just running it with historic time series, but we already have future flows for UK CP18 and also Weather at Home, which is another climate database. And then we have our USARIS collaboration, which I'm really excited about. Thank you.